to today's discussion of Chapter 4, in which we'll be covering product design. And in this lecture, we will be looking at the design process, focusing on the product specifically. And in the subsequent chapter, we'll be looking at the service design in contrast. And within the product design process, we'll look into rapid prototyping and concurrent design, some of the techniques that are in existence, best practices in this field. Look into the various technologies that are used in design of products, how design quality reviews are conducted, then also address the matter of design for environment, sustainability related to design, eco-design, in other words. Then look at some of the tools associated with product design. One of them is quality function deployment, or house of quality. So that's something we'll be addressing in this chapter. And then finally, look at design for robustness. That's where Taguchi loss function comes into looking at product that still deliver value and good output even with extreme conditions. So in terms of trends in both product as well as service design in generic sense, there has been increased emphasis on or attention to customer satisfaction. In today's day and age, more and more products that you look at are focusing on how best to satisfy the customer in this case. So reducing the time to introduce new products, that's another trend that we see before, by the time somebody conceives of an idea of that will be a great product to have, or if a need is identified, from that time to the time a product, a related product is introduced, that time span, the waiting time has been reduced immensely in today's day and age. Reducing time to produce a product is another thing. Not just new product development, but also making sure a design for manufacturing products are designed in a way that they are easy and quick to produce for the markets. Organization capability to produce and deliver the items. So supply chain issues are also addressed, that we are designing products that they are easy to deliver through our company's existing supply chain, or make arrangements so that that aspect of the company is also addressed. Also, in recent years, focus on environmental concern, which is looking at how companies are creating designs, both product and services, which actually have minimal impact on the environment. And then most importantly, create a product that is intuitive to use, user-friendly, so that it doesn't require a training session to actually get to know how to use the product. So in terms of design process, effective design can provide a competitive edge in terms of matching product and service characteristics with customer requirement. So if you have an effective design, you are synchronizing what the customer wants and what that product delivers. So there is still customer satisfaction is ensured in the process. We ensure the customer requirements are met in the simplest and least costly manner, so that customers truly find value in such a product and are likely to buy it again and again, as the case may be. Reduce time required to design a product or service, as I mentioned earlier, and minimize revisions necessary to make a design workable. So that early on with the design of experiments, you are coming with best features in the first edition of the product itself, so that product becomes a success as early as possible. Product design defines, this particular aspect defines how the product will look like, the appearance of it, what are the standards for performance, how this product will be judged against what metric, and specifies which material are to be used in this case, what components, or what specific way of putting it together, and determine the dimensions and tolerances in order to see if things are of good quality in terms of specification wise. In terms of design process, you can see how all the way from idea generation, which is actually being done along with design firms, marketing, which actually gets feedback from customers or people who are interested in purchasing the products for end consumer. Competitors looking at reverse engineering some existing products and seeing what competition is coming up with the products so that we can see what our product is going to compete against. Also, what are the latest technologies and incorporating that into the ideas for new products. Then talking to suppliers to see what new materials are available and what prices. Companies' own research and development, R&D, will also give ideas as to what are the new possibilities, as well as existing customers or lead customers who actually get feedback on beta testing of early products. Then based on this idea generation, you come up with a product concept. That is, this is a new product idea that at least has some feasibility moving forward. And that's where the feasibility studies are done extensively to see the viability of that idea forward. From this feasibility study, one of the output is the performance specifications as to what will be the ideal specifications for such a product. So that, for example, a new computer is being, or new tablet like iPad or next generation product is being produced, one of the key thing would be to see how long should the battery last in the next generation of the product. Maybe the current product did not have a long enough battery life for a truly mobile experience. So that could be one of the examples of specifications that have to be revised for a product to become more successful in the second time around. From this feasibility study, once the performance specifications are outside, comes the rapid prototyping, which is a way of taking the form design and from this coming up with, in rapid prototyping, you do all these three things synchronously, where you come up with the initial block design as to how the product form will look like appearance-wise, and then the second part is the functional design, where the product may not look any in the final shape, but it does exactly everything that the product is intended to do. So over here, for example, if we are coming up with a new computer, a new laptop, form design would just mean creating a shell, taking a laptop shell and saying this is the outside dimensions of, when you hold it, it should look like this, it should weigh around this much, it should have these dimensions, etc., and it should be made of this material. So that's the form design part. Functional design is all the things that you expect that laptop to be able to do are being done in a separate alpha or beta product, if you will, alpha product, but it doesn't look anything like the the final form it's going to take. So all the circuitry that is supposed to go into making sure whatever this computer is expected to do actually is accomplished in this functional design, but the design may be actually sprawled all over the room. It doesn't have to be all nicely packed into one box of the outer shell of the computer, if you will. So these two are totally different. This is a functional design, even though the shape may not be exactly how you would end up selling it to the customer. This may be just the outer shape of how it will look like, how it will feel like, so that you know how to handle the packaging material. And based on all this, come up with a production design in terms of taking into account what manufacturing has to do, how they have to revise the machine settings to make sure a new dimension of laptop case can be created, or new circuitry can be incorporated, etc., which suppliers you have to now cater to, which will add that additional functionality. So from here, you're coming up with the design specifications from functional design, and over here comes the manufacturing and delivery specifications in terms of packaging, in terms of supply chain coordination. And from here, once these two are taken care of, pilot run of final test, making sure the final product survives the testing before it is shipped out, and that's the final design and process plans, and then that's where out goes to the new product launch. So that's, in a nutshell, the entire design process. In terms of idea generation, it can be based on company's own research and development department, or based on what customers have complained about existing products. May that be of their own company's products, or it could be of competitor products. So in addition to that, you get additional ideas from marketing research as to what marketing executives went out, did a survey of potential customers who currently are not companies' customers, but the reason they are not customers is because the current products do not offer them the necessary value for them to become a current customer. So in that case, what is on their wish list? Also, feedback from supplier. If they were to revise certain aspects of a product design, it may reduce the cost, or it may make it faster in production. So a salesperson in the field can also give first-hand account of how customers perceive the product, and collect any feedback from that end and bring it back in terms of what works and what not. Factory workers may offer input about what is the problems in terms of producing a current product and why it tends to fail that often in a specific area. So that could be addressed from the shop floor. New technological developments make it easier to do something much cheaper or much faster, or something which makes it possible which was not possible earlier. So that's where the R&D comes in. And also learning from competitors as to anytime a new competing product comes out in the market, that gives existing companies ideas of how to try to answer back with their own version of the product. And in this idea generation phase, you have several tools. I mentioned reverse engineering earlier, but we'll start off with a perceptual match, which is visual comparison of customer perception on few scales, which are important and I'll talk about, in this case, this is an example of perceptual map of breakfast cereals. So for the customers who actually enjoy breakfast cereals, if they have to rate, if you ask them to rate variety of breakfast cereals on two different scales. One is on good taste versus bad taste, or not so good taste, versus low nutrition and high nutrition. And typically, you can see there is some sort of association, that is, good taste comes, may represent low nutrition because it's more sugar, and that's what one of the products that is offered over here falls in that category. Keep in mind, this is just a perceptual map. It's just in the perception. In reality, some scientists may come and argue that Cocoa Puffs are not really that low in nutrition. That's besides the point. It is in the mind of the customer as to they perceive Cocoa Puffs to be of low in nutrition, but good in taste. So that's why maybe their kids tend to favor that because they like sugar. Rice Krispies may be not so good in taste, but also relatively low in nutrition according to the perception of this set of consumers that were surveyed. Wheaties also is on the leaning towards the bad taste side, but slightly better nutrition. And Cheerios, again, has high nutrition in terms of, better for people's health, but taste-wise, it's not coming up to par. And shredded wheat, even though it's high nutrition, may be perceived as bad taste. So again, that's where one has to figure out is what they would like is to come up with a new idea which may be in this quadrant, which is how can we provide high nutrition with good taste. And one example of that is that product that in breakfast cereal industry is like Fiber One, for example, as they advertise. They're trying to convince the consumers that it's not only high nutrition, but it's actually good tasting fiber. So that is trying to convince the people to change their perception about the Fiber One product choices that are being offered. In terms of other tools for idea generation, one is benchmarking, which is comparing product process against the best in the category. And in this case, it doesn't have to be your own competition. It could be best in that industry or that category, whatever it is that you're looking at. So if it is just the taste, you want to compare it with the best tasting product, regardless of that if it's breakfast cereal or not. So that's where you're looking at benchmarking. Whereas if you're looking at high nutrition, even though you're a breakfast cereal industry company, you do not have to necessarily compare yourself against other breakfast cereal for high nutrition. Then you can see what is the most nutritious product out there and what can we learn from that product, how they were able to make it and package it and still retain the good nutrition in it. So maybe something can be learned from that, from the best in class over here. Reverse engineering is strictly focusing on your competitors' products. So if you're a breakfast cereal company, you actually take apart, open up a box of a competitor product and actually chemically analyze their cereal and then see what are they offering, or they're adding another toy in the cereal box, plus look at the amount of sugar they're offering, look at all the other vitamins, minerals that are there, and accordingly make an assessment of what it does it, how much cost it may have and how much production process uniqueness is there, so that if they have to come up with the equivalent product, company can then estimate what will it take to offer a substantially competitive product in that category. Now, feasibility study, the next step that we mentioned, you typically use market analysis, go out, survey do a marketing survey of customers and other stakeholders in this case. Also do economic analysis. If we are going to come up with a new idea, how much will be the ingredients cost? How much will be the cost of changing production process, machines that have to be added, or maybe a refrigerator is needed to have a freeze dry certain parts. For example, there are cereals which actually include frozen or freeze-dried fruits in it now, and so those will be how much that additional step will cost in terms of economic analysis. Then we have technical and strategic analysis. Technical analysis is looking at making sure will it still survive the typical life of a breakfast cereal on a shelf before it actually is opened, how long will it still retain its taste, etc. How big the bag should be. So a lot of cereal companies, what they actually do these days technically is rather than increasing the price of the cereal, they reduce the size of the cereal box, which perceivably in the minds of the consumer, they don't realize that earlier they were buying 24-ounce box of a cereal. Now what they're getting is 20-ounce without realizing that a company actually reduce the size, thereby reducing the cost. And so that could be a technical as well as strategic decision on their part. Technical on the part that maybe it's easier to fit more boxes in a container and truck more boxes per shipment. And also it fits nicely on the shelf as well as it fits nicely in the kitchen pantry on the consumer side. And therefore, usage-wise, it retains its freshness. If it's smaller enough, then it gets eaten up in good time before it has a potential for spoilage. So that could be the technical analysis. Strategic analysis could be the company is maybe emphasizing the new direction of aiming towards freshness as their motto in terms of good taste and freshness. So that maybe works well in that regard. And then from all this comes the performance specifications that are needed in terms of making the new idea work well in the industry. Rapid prototyping, as I mentioned earlier, in this case, testing and revising a preliminary design model. Build a prototype. It's like a first draft of what the product will look like. And that's where you do the form design, functional design, and production design that I mentioned earlier. Then test the prototype, see how it works, revise the design to see, oh, this printing of the breakfast cereal box, the printing is not very eye-catching. So maybe we have to improve things in that case, and then retest it accordingly. Now, in terms of concurrent design, idea of concurrent design is to actually, in traditional companies, you have customer talking among themselves, and if marketing person gets their survey, they do not actually see them face to face, but they just receive the survey feedback back, which is sent via interdepartmental mail to the design engineer, telling them what the performance specifications should be. And from that information, as the design engineer sees fit, will redesign the product in isolation and send it to manufacturing engineer, which will, based on the design specs, will come up with the manufacturing specs, and the actual production personnel may produce this revised product. By having this off-the-wall interaction, this is sequential design, there is hardly any communication. It's almost on an asynchronous mode. So by the time production personnel receive this manufacturing specs, they may be far apart from, very distant from what customer really wanted. So that is the problem with current sequential design methodology. In concurrent design, you basically bring all these parties to one table, or bring them all face to face, or in a virtual online meeting, whatever the case may be, so that they can actually have a synchronous environment to discuss as to what is needed in this revised product. So this really works well in that scenario. So this whole field of engineering is basically the simultaneous development. I'll just cut it. Basically, they're my kids, since I'm babysitting them also. It's okay? Okay. So I know you. Okay. So concurrent engineering is the simultaneous development of product design functions with open and interactive communication among all members, as I pointed out earlier, where they are actually trying to come up with a new design in this case. Now, it does go a long way in reducing time to market, decreasing the cost, and improving quality and reliability of the product, because all the questions can be answered at the same time for whatever the customer's wish list is, that can be correctly transmitted, that information is transmitted to the design engineers, who can actually maybe create an impromptu design which manufacturing can provide input on, whether or not that will be doable in their current machines, or manufacturing engineer can also point out what is possible, what's not, and production personnel can talk about how long will it take, or this will be harder, it will increase the time to produce one particular product, and maybe there could be some sort of consensus they can arrive at, where actually listening to what customer really would like and bringing that realizing that in terms of a new product. Now, in terms of form and functional design, basically form design is how the product will look, as I mentioned earlier, which is, if you remember, we talked about the laptop computer actually coming up with the specific dimensions of the outside box so actually coming up with the specific box in which the laptop will be encased, whereas functional design is how the product will perform in terms of reliability, maintainability, and usability. So here is an example from Japan of a product which is like thinking outside, or in this case inside the box, of they really, this is based on the needs of the stores there. So if you look at watermelons typically have a spherical shape, which makes them harder to put it on a shelf unless there are other constraints around them. They may roll off, or they may take a lot more space between one watermelon and another one. So to solve this problem, one of the innovative approaches was to actually grow the watermelon in a box. So that way they end up taking a more cubic shape, and thereby easier to stack right next to each other, highly dense environment in terms of shipping, more watermelons reach safely at the destination, also take less shelf space. So it's a very simple example of how the product should look like and how they should perform, and in this case performance is during transportation as well as retail shelf life, so that even though in eating it's exactly the same watermelon, but it's the design in this case is innovative design of how it looks like from outside. Okay, so in terms of production consideration, as I mentioned, you look at manufacturability, which is the ease of fabrication or assembly, which is important for cost, how much the product will cost, what the productivity of the person will be in terms of producing the product, and the quality of the actual product. Durability, which is product's ability to function even under hard wear conditions or extreme usage conditions. So even if it falls on the floor, it still works. Like you have example will be a Timex watch, which as they say, it takes a licking and keep on ticking. That's the example of durability. So any extreme sports products will have durability will be a desirable criteria. Reliability, on the other hand, its distant cousin of durability, is the product ability to function over its life under normal usage condition. If you say a light bulb is on average expected to last for 1,000 hours, if it does, that's good, reliable measure of the life of the product. In terms of usability, is the ease of use of a product or service, ease of learning how to use that also is one of the metrics of usability, ease of remembering how to use it. So if you use it infrequently, you shouldn't forget how to use it in between uses. Frequency or severity of errors that are occurring in terms of its production or during its usage, so that also will impact the usability, and user satisfaction with experience as to how they like it. There are certain regulation and legal considerations as well, and certain area which is product liability, which is manufacturer is liable for any injuries or damages caused by faulty products in this case, and also Uniform Commercial Code, that is in the United States on product area implication of merchantability and fitness, that these are saleable products under Magnuson-Moss Act of 1975. Any product has an implied warranty. I think at least over $15, product over $15 has a implied warranty of merchantability and fitness, that they are fit to use as well as they are saleable in saleable condition. Now, in terms of computing reliability, it's pretty straightforward. Reliability calculations, when components are in series, when you put two components together, the first component has a reliability of 90%, second one reliability of 90%. Put together, you have to just simply multiply the reliability numbers. 90% times 90%, that's 81% is the new reliability. Whereas, so in this case, the reason why the reliability reduces of the entire system is, in order for the system to work, both the first component as well as the second component. So in this case, first and, so the key word over here is and. It's an and environment. That means you have to multiply it to come up with 81%. So it's this is the number when 81 out of 100 times where both first component and the second component will be working. In contrast, when you have components in parallel, this represents a backup system. So R1 and R2. So in this particular case, you have component 1, which has a 95% probability, but then you're adding another backup system. In case this does not work, you have this one working. So you have 95% of the time this will work. So this is the situation of A or B. So this is OR, as compared to in series where we have AND, this is R1 or R2. So in that case, the final reliability is 95%, which is the number over here, plus in the case it does not work, which is 5% of the time. In 5% of the time, then we have the fallback system of 90%. So 5% of the time, then we have to go to that 90%, okay? So 95% plus 5% of the time times 95, so this is 0.995. So that gives you much higher reliability. So in this case, in parallel, only one of those two has to work in order for the system to work, and that's where the reliability increases. So the system reliability, for example, if you're calculating the number over here, you have system in series plus in parallel. So it's easy to calculate first the parallel part, which is right here. So you have 92% plus 1 minus 92%, so 8% of the time, then you rely on that 90% over here. So 90 times 0.8, so that is 92 plus 0.072, that's 99.992, that is what you have over here. And then multiply these three numbers, so you have 90.98, 0.99 times 0.98, all three multiplied gives you 0.951. So that becomes a system reliability. Now, that's a system reliability number, so easy to calculate. I also want to introduce to you a system availability number. And system availability is used where you have two different numbers. Mean time between failure, how long between one failure occurring and the next failure occurring, versus mean time to repair. How long does it take whenever so for example, in office equipment, you have fax machine or a photocopier for the in office department. Maybe it's listed as that machine breaks down once every month, okay? And the question is, once it breaks down, how long does it take to fix it? Maybe it takes 2 hours to fix it. So you're looking at the actual time between failure is 30 days, because every 30th day it breaks down on average. So whereas it takes only 1 hour to fix it. So in this case now, you can easily, and you multiply 30 days with 24 hours, to get the number of hours before the next failure. So that's an example, but let's look at a specific example in this case. You have 3 different providers to see which one, let's say it's a network system. So which one should you go with if you want maximum amount of uptime of your network? So you have mean time between failure is 60 hours. So after 60 hours on average, the system will break. And in this case, it will be down for 4 hours. Whereas over here, the second one is every 36 hours, it will, between failures. But mean time to repair is only 2 hours. And the third one is 24 hours. The system, on average, breaks down once a day. And in this case, the time to fix is 1 hour. So you can easily see 60 divided by 60 plus 4, that gives you about 94%, whereas this is 36 over 38 at 95%, and finally 24 over 25, which is 96%. So somebody who would like a company that would like maximum uptime of their network will probably go ahead, and it doesn't matter how often it fails. What matters is how quickly can they fix that problem. So that gives you the maximum availability. So even if it, this one failing every 5 days, but it takes 4 hours to fix it, whereas this one failing every 24 hours, which is, but only one hour to fix it. Now, in terms of production design, you're looking to focus on how the product will be made. And so now we're getting into the actual production of the product. So in here, there are 3 different areas. Specifications are important. Specifications are detailed description of the material, parts, products that are going to be produced, with specific measures for physical dimension, weight, density, pH rating, whatever, viscosity, all the physical attributes of the product that are going to be used. Simplification, so for example, if a new toothpaste is being designed, so you will look into exactly how much the weight of the packaging is, what the density of the paste which will go in the toothpaste is, the specific pH rating, all those specific information will be there. Simplification, reducing the number of parts, assemblies, and options in a product so that you have least amount of time to taken to produce the product. So it is quickly, you can ramp up to high production as needed. And the other reason for simplification is so that you end up using straightforward processes which everybody is familiar with and already trained in. So you don't have to have specialized training for producing these products. Third one is standardization, using commonly available and interchangeable parts. You don't try to come up with unique parts which become pretty expensive to source, as well as unreliable inventory available for those parts. So that's why standardization is like using 8.5 by 11 sheet of paper for every single assignment that you have. That makes it easier for you to take those college bound or wide ruled paper and use it in any folder or any jacket that you may have, and easily interchangeable. Modular design is another concept which combining standardized building blocks or modules to create a unique finished goods. So for example, in case of wireless drill, you can easily take the battery off and put another battery. That's an example of modular design. Or you can use the same battery to use a screwdriver, or you exchange the screwdriver bit and put a drill bit in it, and things like that. So those are all examples of modular designs that can be created for typical home implements, if you will. It allows for easier diagnosis and remedy of failures, because we are just dealing with a common design which everybody is familiar with. Easy repair and replacement and simplification of manufacturing assembly in this case. Now, in terms of, we have already talked about, in production design consideration, we talked about reverse engineering, which is taking apart the competitive product to discover product improvement. But let's talk about specific other aspect, design for manufacture, designing the product in a way that it's easy to produce in the existing production floor that you have, shop floor. And then other ideas, design for disassembly, designing product in a way that it's easy to disassemble so that you can take apart the product at the end of life and extract what are still valuable product parts out of it and remanufacture them and use them again, or in case of ink cartridges in printers, those are examples of design for disassembly. Those are easy to take out and use in other cases. And then other concept is designing for supply chain, extending the design for manufacturing to the broader scope of entire flow of material through the supply chain. So in this case, emphasize reduced design complexity. So idea is you can think of John Deere makes use of multifunctional design teams that include outside suppliers so that it's easier for them to also ship the product to John Deere for making those farm equipment, tractors, etc., and shipping them to their dealers. So Selectron negotiates capacity level. So in this case, supplier capacity is actually negotiated. They don't really tell them what will be produced, but maybe 80% of the capacity of next year would is what Selectron may desire and contract them out for. So in this case, example of design simplification is you can see original design may have so many numerous parts. So in this case, you can see a much more intricate involved production process of making sure every single nut and bolt and washer goes in the right place. And even during the use, you can see all it takes for one nut and bolt to become loose for this entire contraption not to work as intended. So the revised design is one piece base and elimination of faster. So you can see all the nuts and bolts are gone. And so this is not three pieces, but now just one piece, which is just kind of folded over. And then you have, so from multitude of, you have over about 20 different parts over here. Now you're down to 1, 2, 3, 4 parts. And now you can even go further, and final design could be that you don't even need to have these two parts up there. And that could be just more of a snap in type of final design, push and snap assembly. So again, it's just down to two parts, simplify and make it easier to produce, if you will. So final design and process plan, it's detailed drawing and specification for new products or services. So process plan, workable instructions, necessary equipment and tooling that is needed, how the machines have to be revised to do the work, component sourcing recommendations, job description, and where are you going to buy the product from, what type of job will be required on the shop floor so that we can hire the right people in this case, computer programs for automated machines that will be needed in this case as well. Now, in terms of various technology that is needed in design, so you have computer-aided design. So in this case, example of that is SimCity that many students may be familiar with, like a video games where you can actually design the entire society based on simulated individuals in the video game. So computer design, in this case, assist in creating modification, analysis of a design. So there are a lot of software out there that allow you to design your own landscape or remodel your own house, what will the revised or version of the house may look like later on. so without actually doing any changes. Computer-aided engineering is testing and analyzing design on computer screen to look into, will this design still survive the brunt of 40-mile wind, 80-mile wind? Will this roof survive if we were to put that? Or if we decide on an alternative style of roof on the house, will that survive the thunderstorms or heavy winds that this region faces, for example? So that's where computer-aided engineering, which actually can run simulation to see if that will be possible. Computer-aided manufacturing, which is actually now you're using computers to manufacture certain things. So the classic example of that is the numerically assisted, in this case, components that we all use in the kitchen, microwave, for example. All we do is push some buttons, and the computer in the microwave will decide to heat the food in there for a certain amount of time, what we have entered the data for. And that's so almost it's cooking the food, manufacturing the product, if you will, in this case. Product lifecycle management, managing the entire lifecycle of the product and seeing exactly how it's going from inception all the way till end of life. And then collaborative product design is another tool of working together to come up with the product design, as I mentioned, in concurrent design methodology. And in details of that, in collaborative product design is you have multiple teams, a software system for collaborative design development among training partners. So in this case, you manage data, set up project workspaces, and follow life cycle of the product, accelerate product development, and also addresses the various product launch issues and improve the quality of design. So in this case, designers can look into virtual reviews and what-if scenarios. What if we were to do this? How will the product change? Will it look better? Will it perform better in that case? Assign and track design issues. So certain teams or group of people can focus on one aspect of the product. Others can focus on other aspect of the product in this case. Communicate with various suppliers and manage product documents. Then you have design quality reviews, and in this case, review design to prevent failure and ensure value. And certain tools in this case are FMEA, which is failure mode and effect analysis, that used a lot in industrial engineering origins, but now it's a mainstay even in operations management area in companies where they have to look at analyzing product failures as to why this failure occurred and what can be done to prevent that in the future. Then you can also use the fault tree analysis to visual method for analyzing interrelationship among failure, and then also value analysis, help eliminate unnecessary features and functions. So for example, the following slide is an example of FMEA on potato chips, where you can think of failure mode is stale, and what is the cause of why potato chips became stale. One example is low moisture content, expired shelf life, poor packaging, effect of failure, tastes bad, won't crunch, and again, what can be done to fix it. So you can see that as an example of identifying specific causes, what is the effect of that, and if the effect is important enough, take the corrective action. Fault tree analysis, as I mentioned earlier, is a visual depiction of what's happening and what is the undesirable result, undesirable solution versus what's the acceptable solution. So you can actually go down the right path. And the value analysis in this case is eliminate unnecessary features and functions that you have. Try to see, is every part of the product or every feature that you're incorporating truly adds value, or is it just there because it was there in the previous version of the design and we just never took it out. So a lot of times some students who buy Microsoft Office for example, in a hypothetical scenario, may not be using Microsoft Outlook in there, but it's still packaged because that's how that software was designed. Now, that is not to say that many others do not use it. I'm just giving as a hypothetical example. But if for a certain company, they may have the option of just removing that out or just separating that for a specified market, if you will. So this is where you look into and see what are the features that are necessary, what are deemed unnecessary, used by multifunctional design teams, define essential functions of an item, and then what is the value of that function, and what will it cost to provide that function if it's needed. For example, new vehicles that are coming in, how much will it cost to actually provide keyless entry, and how much value does a customer place on having that keyless entry is an example of value analysis. Compute value, cost ratios, and then design work teams in this case. Next, we'll look into the design for environment and extended producer responsibility. So in this case, design for environment of a product or eco-design is designing a product from materials that can be recycled. So making sure you are using materials that are not harmful for environment in terms of after end of life. Also, if possible, design using recycled material that has been used earlier. So a lot of times you see paper that is available for printing paper, which always says, for example, 20% recycled material. That's an example of design from recycled material. Design of ease of repair. So it make products that are easy to repair. All the items that actually have high failure rate, all the parts which tend to have high failure rates, make them easily accessible in a product. Minimize packaging so that you are not wasting a lot of space in the garbage by throwing the packaging of the product. Minimize material energy use during manufacture, consumption, and disposal. So reduce the carbon footprint of the company in terms of, and extended producer responsibility is hold the company responsible for the product even after the useful life. That is, if somebody were to buy the product and after the useful life of the product were to dispose of the product, the harmful parts in that product, electronic product, for example, cell phone, etc., that should not damage the environment. That should be part of the extended producer responsibility. So that's where the new concept is going. So in this case, you can look into different type of environmental aspects. You look at input in terms of sourcing, less material, recycled material, organic material, etc., non-toxic, renewable, durable material, and then you have less use of energy during motion of transporting as well as manufacturing the product. So lower carbon footprint as well as energy efficiency or during consumption of the product, longer life, so it doesn't have to be replaced that often. Easy to repair, recyclable, etc. So you can see, and if as much as possible have the closed loops going in. So this green area or environmental impact goes much further than just traditional manufacturing. You have the green sourcing, so you're using less material or recycle. Then green manufacture, as I mentioned, reducing the carbon footprint and reducing the waste produced in this case. Green consumption, product use of energy should be least, and product recyclable and maintainable, and then if possible recycle and reuse. Another important tool that we are looking at is quality function deployment. Translate the voice of the customer into, so this is a tool also known as House of Quality, is a tool to actually translate what is the customer's wish list and translate that into meaningful design specifications that can be incorporated in the new product. So in this case, display the requirement in a matrix diagram and series of interconnected figures or houses as they're called. So House of Quality looks like a house where you have a bay window which actually lists all the what's, which is the requirements of the customer, what customer would like, the voice of the customer. And over here, what is the important rating of all the way from 10 to 1 or whatever the numbers are. And then how these requirements can be translated into appropriate design characteristics is the indication over here. And then we also try to look into the roof of the house is the trade-off matrix, that is how one design characteristics is affected by another one over here. Is it positively or negatively associated with that? So inside of the house is the relationship matrix, how well customer requirements align with the design requirement. Competitive assessment, which is looking at how companies do compared to their competitors in this case. So based on that, after looking at importance, out comes the target value as to where we'll have the biggest bang for the buck for improving things. So you can see as an example, in first step, you come up with competitive assessment and customer requirements, the two sides of the, this is what we are calculating at. And in this case, you look at a product which presses quickly, removes wrinkles, does not stick to fabric. So we would like, garment to iron, the iron that is being designed, it should iron well and easy to and safe to use. So in this case, the cloth iron should automatic shut off, heats quickly, cools down quickly, etc. So those are all the wish list, and then it should do its job well, does not spot fabric, scorch fabric, provide enough steam, all those things. So in this case, you're looking at how the competitively X marks your own company and A and B are the competitors. So in this case, you can see presses quickly. Our company does a better job currently as compared to A and B. Whereas you can see in some cases not too heavy, that's where other companies are doing a better job. So after those are being done, you can see how what customers would like relates to what are the design criteria, and from that you can come up with how various design specifications relate to each other, and then based on that you come up with the specific target changes that can be possible that you have. And then this is the completed house of quality, how it looks like in real life. And you can use that for a variety of things, variety of features in a product. So you can use that for one type of product characteristics, which is iron, the iron portion of the product, in terms of packaging, in terms of parts, in terms of process, etc., and improve things. Benefits of quality function deployment: it promotes better use of customer demands and promote better understanding of design interaction. Involves manufacturing design process and provide documentation of design in this case. Now, the last topic we have is design for robustness, which is robust product designed to withstand variations in environmental conditions. So even if you use the product in extreme heat or a hazardous condition, it still will perform without providing any fault or defects. So robust design yield the product service designed to withstand variation in use. So sometimes people may end up dropping products or end up using the stapler with much more force than required. And every time if it delivers a quality stapled stack of paper, that will be a robust design of that stapler, for example. Controllable factors, design parameters such as material use, dimensions, etc. And uncontrollable factors are user control. How long does somebody uses the product? That's something not in the control. So in that case, you tend to look at tolerances. What are the allowable tolerances that you have? Consistency, how consistent are the errors and how long will it take to correct them? And then consumer preferred product characteristics that near their target value. So one tool, and the last slide that we'll be focusing on over here, is the Taguchi loss function requirement. So if you look at it, traditionally the quality loss, as long as traditionally it is lower tolerances and upper tolerances, so the customer would like everything between this area, and as long as traditionally you stay within this zone, shaded region, customer is willing to accept the product, but outside that, customer will reject it. So traditionally, you look at the quality loss will be immense to the manufacturer. That is, if they produce lower than the lower tolerance limit or higher than the upper tolerance limit, their material will be rejected. So whereas over here, what Taguchi said was, this product, even if it is produced in here, it still is off target and will not do a good job over time in terms of robustness. So that's the value added in this case. So this is used a lot in design for Six Sigma. Idea is that there is a sliding scale of loss of quality, and ideally what we'd like is to put it on target. So this is where we stop, and we'll come back, and next time we'll look into service design in the future lectures.